Hey everyone, and welcome. I'm your host, and today we're doing something just a little bit different. I want you to step into my shoes as a 20-year veteran plant operator. We're going to turn this explainer into a definitive masterclass on one of the most stressful issues you can face in a high-purity facility, which is diagnosing and treating electrodeionization, or EDI, performance degradation. Look, if you work with ultra-pure water, you already know that when an EDI module starts failing, the clock is ticking loudly. So we're going to break this down methodically, slowly, and clearly, exactly like we would out there on the plant floor. All right, let's dive into this. Here's our roadmap for the session. We're going to start with a quick tech overview, move into the incident itself, hypothesize the causes, do some root cause isolation, walk through the actual troubleshooting steps, and finally wrap it all up with a summary and conclusion. All right, part one. The ultra-pure water and EDI technology overview. Let's get to know our patient. Think about the absolute gauntlet our water has to run through. We start with raw water, pushing it through multimedia filters, then into cartridge filters, and then through reverse osmosis. But you and I both know, RO alone just isn't enough. That is exactly where our EDI module comes into play. It's an absolutely critical polishing step. It uses electrical current to physically drive ions out of the water, prepping it for that final UV treatment to achieve that incredible product resistivity of greater than 15 megaohms. The EDI is the heavy lifter here for achieving that ultra-pure quality. And here's the hardware we're diagnosing today. It's the Ion Pure LX High CEDI module. I mean, just look at it. It's a beautifully robust piece of engineering. But listen, even the best equipment running continuously under intense electrical and fluid dynamic stress requires expert oversight. By design, it creates a bacteriostatic environment internally, which is fantastic, but it's not invincible. And when things go wrong inside that box, they tend to go wrong silently. Moving on to part two, the incident, specifically performance degradation. Picture this. You're out on the plant floor. It's the middle of a critical production run. You glance up at your monitoring screens and your stomach just completely drops. You see this number. Your product water resistivity has plummeted below 5 megaohms per centimeter. Let me be crystal clear about this. In an ultra-pure water facility targeting over 15 megaohms, a drop below 5 is not just some minor fluctuation. It is a severe degradation event. It threatens the quality of literally everything your plant produces, and it signals an immediate risk of a total production shutdown. So let's define our core symptom. The product water resistivity is tanking, but here's the catch. When you check the feed water, meaning the RO permeate coming into the module, it remains at perfect design specs. The conductivity and CO2 levels are totally fine. This right here is the central mystery of our incident. The feed water isn't the culprit. That means the fault lies entirely within the EDI module's internal environment. We're dealing with an isolated failure. Which brings us to part three, formulating a differential diagnosis. Time to play detective. Whenever I see this kind of degradation, I immediately run through four primary suspects in my head. First is resin aging. Over time, the ion exchange resin inside just loses its functional groups. Second is internal scaling, where minerals build up on the membranes. Third, system fouling, which is usually biological or particulate matter choking the flow. And fourth is straightforward operational error, specifically incorrect DC current or pressure settings. If you're a junior engineer listening to this, write these down. 99% of your EDI headaches are going to live right on this list. Let's move to part four, isolating the root cause. Time to run some tests. You always have to start by asking the most basic, yet honestly the most frequently overlooked question before you go tearing apart a complex piece of machinery. Is this just a simple instrument error? The very first step in the manual's troubleshooting flowchart asks explicitly, is the product flow meter incorrect? Think about it. If your flow meter is feeding you bad data, your module's residence time and all your performance metrics are going to look completely wrong. The solution here is super straightforward. Recalibrate or replace that flow meter. Always, always verify your sensors before you blame the module. Okay, so let's say the instruments are reading perfectly true. What's next? We ask if the operating parameters are misaligned. We're specifically looking at the pressure dynamics inside the module. Those internal pressures dictate exactly where the water flows, and if they're wrong, your quality is going to tank. The troubleshooting flowcharts give us a golden rule of thumb. You have to ask yourself, is the reject outlet pressure greater than the product outlet pressure? If it is, well, you're practically pushing dirty reject water backward into your clean product stream. You must adjust your product outlet to be 2 to 5 psi higher than the reject outlet. It is a surprisingly simple mechanical adjustment that can instantly restore your water quality if things have just drifted out of spec. But what if the pressures are dialed in perfectly and the quality is still dropping? That's when we have to investigate the physical health of the module's interior. We need to ask, is biological fouling or particulate pluggage choking the system? To figure this out, the manual points us toward a specific test. Does a multi-agent cleaning help? We clean the CEDI with a combination of sodium chloride, sodium hydroxide, and either percarbonate or hydrogen peroxide. Now, if you perform this extensive clean-in-place procedure and it still doesn't restore your flow or quality, that tells us something really critical. It indicates severe particulate pluggage or biofouling, which means you have to step all the way back and evaluate your entire system design and your upstream operation. That brings us to Part 5, Step-by-Step Troubleshooting and Recovery. So here's your concrete remediation game plan. Step 1, perform a specialized CIP using acid and base, exactly as recommended by the manufacturer, to clear out any scaling and fouling. Step 2, recalibrate your DC voltage, amperage, and internal pressures based on your feed water conductivity. And Step 3, and look, this is just a tough reality of plant operations, if your module has been running for 3 to 5 years, that resin might simply be depleted and oxidized. You cannot clean dead resin. At that point, the module just has to be replaced to protect your overall production. Now, how do you actually know if you're winning the battle during recovery? You track your data like a hawk. The manual insists on comprehensive monitoring. You need to be logging your DC voltage, your DC current, product and reject flows, and of course your product resistivity. You have to track this on your log sheets during startup, during regular operation, and especially after a recovery procedure. You're doing this to ensure your module resistance, which is just your volts divided by your amps, is actually stabilizing. And finally, Part 6, Summary and Conclusion. Let's look at the procedural approach. If you take absolutely nothing else away from this explainer, please remember this. Methodical, unpanicked troubleshooting is exactly what separates the novices from the 20-year veterans. Systematic diagnostics prevent massive production shutdowns. Period. When you see that resistivity drop to 5 megaohms, you don't panic, you rely on the data. You rule out the simple instrument errors first. You double-check your pressure differentials. And if necessary, you execute your CIP protocols strictly by the book. I want to share a fundamental operating philosophy pulled directly from the Ion Pure ADI maintenance manual itself. It says, prepare a list of all problems encountered. Have your monitoring log sheets at hand. Human memory is flawed, guys, but your log sheets are the vital signs of your plant. Good, consistent documentation is genuinely your absolute best diagnostic tool when things go dark. So I'm going to leave you with a final challenge today as an operator. Are you checking your plant's log sheets today? Are you looking out for those slow drifts in pressure or current before they turn into a 5 megaohm crisis? Take this proactive mindset back to your facility immediately. Thanks for joining me for this explainer, and stay vigilant out there on the plant floor.